For problem number 4, we have a satellite placed in circular orbit around Mars, and we need to derive an expression for the orbital speed, assuming that the orbital radius is r. So this is proved for you in your notes, but it's a good one to know how to do by heart. You know that the force of gravity is equal to mass times centripetal acceleration, and that the force of gravity is G big M little m over r squared, which is equal to mass times v squared over r. A lot of this will simplify, and you end up with v is equal to the square root of g m over r. So that's your orbital speed, something that I highly encourage you know how to derive. Derive an expression for the orbital period. The orbital period is the fact that velocity is equal to 2 pi r over period, which is a full circular rotation, and then over the time it takes for one rotation. But we have to isolate the period. And in this scenario, what we would do is, since they are both the same velocity, we can plug this velocity in here, and we get the square root of gm over r is equal to 2 pi r over period. And then we want to solve for period, so I'm going to square both sides. And then I'm going to bring the t squared out on its own. So t squared is equal to, and then I'm going to bring this r to the r squared to get r cubed, and then gm at the bottom. And then we're going to take the square root of everything. I have some squared values here that I can pull out, and then I've got r cubed over gm as our equation for the orbital period. And then part C says the orbital period of the satellite can be synchronized with Mars's rotation, whose period is 24.6 hours. Determine the required orbital radius for this to occur. So what we have is a period of 24.6 hours. We always want to convert that to seconds, so that's 3,600 seconds, and that would give us 88,560 seconds. From there, we are going to solve for the radius, and so we're going to start with our period equation. And then isolate the radius. So let me bring the 2 pi over. And then I'm going to square both sides. And then I'm going to bring out the r cubed. And then from there, it's just a matter of plugging in values. My r is going to equal the cubed root of t squared times g times the mass of the planet, 4 pi squared. And if I plug all of those values in, so my period is 88,560 squared. G is 6.67 times 10 to the negative 11. The mass of the Earth is 6. Is this the Earth, or it's Mars actually? The mass of Mars is 6.4 times 10 to the 23rd power. And then all of that is over 4 pi squared. And then in the end, hopefully you get 2.04 times 10 to the 7 meters if you plug everything into your calculator correctly. This last part says to determine the escape speed from the surface of Mars, and that is an equation that you also got in your notes. I'm going to work through the derivation for you. I think it's good practice. So we're going to use the conservation of energy equation, and we're going to keep in mind that U is equal to 0 at infinity. And so because of conservation of momentum, if my momentum is equal to 0 at infinity, we're going to call the total energy equal to 0 at infinity. So based on conservation of momentum, if we're starting at the escape orbit, I would have some kinetic and some gravitational. And then if we're looking at infinity, that would equal 0. We're going to plug in our equations of 1/2 m. This is my escape velocity squared. And I don't know why I put the negative here. That should not be negative. This one should be negative. Negative g big M little m over r is equal to 0. And then we are going to solve for the escape velocity. So here we've got mv escape. I don't know why I put a p there, but escape squared all over 2 is equal to g big M little m over r. So v escape is equal to, I'll call that v escape squared, is equal to 2g big M little m over r little m, which simplifies. And then we just take the square root of both sides, and that's the square root of 2gm over r. If we plug in our values, is equal to the square root of 2 times 6.67 times 10 to the negative 11 times the mass of Mars, which is 6.4 times 10 to the 23, all over the radius of 3.4 times 10 to the 6, and that whole thing is equal to 5,011 meters per second.